let's talk about design principles. Design principles are one of the most fundamental things I find useful when it comes to both strategic and tactical design, but more so during the tactical design phase of software development. We talked about strategic versus tactical design in other presentations, but here we're going to focus on simply the design principles that are so fundamental. Using some of these design principles, what I consider to be very important fundamental principles, helps us a great deal to create better software, better quality of software. So we'll focus on some of these principles and not only learn what these principles are, but also to apply them and also to identify them on different code examples. So let's get started. The very first question to ask is, how do we measure the quality of design? How do you say a design is good or a design can be better than what it is right now? Well, I'm going to say my design is really good from the point of view of object-oriented because I'm using objects. Well, that quite doesn't cut it, is it? We could say the design is really good because we're using, name a language you're interested in. Well, that doesn't really say it also. Well, my design has to be really good because look at the wall, I've got UML diagrams all over, isn't it? Well, unfortunately, that doesn't tell us it's a good design also. Or you could use a measure that I came across once with a colleague of mine. He said my design is good because I created it. Well, of course, we don't want to use such standards as well. Those are called egocentric measurements. That doesn't help also. So the question is, how do we measure the quality of design? Well, the very first thing we need to come to realization is that we simply cannot create really good quality design in one setting. Design is something we have to work and we have to evolve. So we have to evolve towards a better design than trying to create a better design in one sitting. And this is something we have to just get into terms. If you're of the opinion that you can sit down and design once and write code once and be done with it, you're going to be in for a real big disappointment because software doesn't get written, software gets rewritten. So we always have to write something and rewrite it. Much like how when we write English, for example. When I write books or when I write articles, it's never about writing it, but it's always about rewriting it. I write something and I rewrite it several times over. Then my editor looks at it and it gets rewritten by me again after the feedback. And then my technical reviewers look at it and again it gets rewritten. So there are parts that get written and rewritten several times. And code is exactly the same way as well. Good code is not written, good code is rewritten. And so design is something that's got to be done in a very incremental and iterative process. We have to create something, get a feel for it, and we got to come back and evolve it. It's very, very difficult to design. I'm going to even say it's impossible to design right the very first time. So how do we really go about measuring the quality of design that we create? We could argue that a better quality design is something that's easier to change, easier to evolve, but unfortunately that's more after the fact. When we finish designing and when a need for evolving the software arises, we can say, look, I was able to easily maintain it and evolve it, so that was a good design. Yeah, that's great. But what if we are not able to evolve it or easily maintain it? At that point, we could point out and say, well, that was a bad design, but I'm sorry, that's too late. We want to really be able to create a better design proactively rather than saying, oops, that one really turned out to be really bad. So how do we really measure the quality of design proactively so we can start creating better quality of design? That's the question we want to focus on. So there are a number of design principles we can focus on, and also there are certain design metrics we can look at. These are rather very simple metric we could actually use, but we got to be conscious. We have to pay attention to the code that we are writing and the design that we are creating in it for us to be able to use it. If we blindly plow through and simply write code that simply produces results, then we end up creating poor design along the way and we don't even know it or we don't pay attention to it. So we got to really be conscious and careful when creating code and design and to evaluate it constantly. So one of the very first measures or metrics to think about is the measure of coupling. Now, I'm going to say a heavily coupled system is a crippled system. It becomes really hard to maintain. The more the coupling is, the more difficult it is to maintain the software we create. So as a result, as we develop applications, we should strive to lower coupling. And in addition to lower coupling, if we can, we should actually decouple. Removing coupling is far superior than having coupling. And if we cannot remove the coupling or the dependency, it's better to have a loose coupling rather than a strong coupling. Given a dependency on a concrete class versus a dependency on an interface, a dependency on an interface is a lot better than a dependency on a class because it's a loose coupling when it comes to depending on an interface. Now, why is that? If you depend on a concrete class, you cannot really vary that abstraction or implementation because it is concrete. And you can, of course, inherit from that concrete class below, but there is a limitation to how much you can implement and inherit from that implementation. But on the other hand, if you depend on an interface tells you what it does but never does anything real, and there are classes that can implement very differently the actual behavior prescribed by the interface. That gives us a lot more extensibility. So it is better to avoid coupling if you can, but if you do have to couple, it's better to couple to an interface rather than coupling to a implementation. Of course, this is mainly centered around statically typed languages. In dynamically typed languages, we don't really care so much about interface. We talked about design by contract versus design by capabilities. So in that case, we really care about some class or object that implements an implicit interface rather than an explicit interface, meaning that it implements a certain features or functions you expect, not really designed by contract where you comply to an interface at the compile time. So when it comes to coupling, we want to lower coupling as much as we can. But one of the things that increases coupling is inheritance. So inheritance directly puts us in front of coupling because a class is inheriting from another class. That's direct coupling on that particular concrete class that or an abstract class depending on what you inherit from. So inheritance increases coupling, and that is one of the disadvantages of inheritance. So we got to use it very judiciously. We talked about inheritance versus delegation in other presentations, but the point really is that we have to be very careful in how we really come up with these kinds of dependencies. So when it comes to coupling, we want to really avoid strong coupling and we want to move towards a loose coupling, and we have to design for the weakest form of coupling as much as we can. When it comes to cohesion, another term that we need to be very comfortable with, cohesion is the degree of connectivity among the elements. In other words, cohesion is talking about how much the different parts of an abstraction are related and work with each other. So in other words, a cohesion makes a class very narrow and focused. Another term for cohesion is single responsibility principle. So we are trying to really make the class focus on one thing, and we need to really weed out things that don't belong here into other abstractions. And when we are done, this function becomes extremely cohesive. So cohesion is where we are trying to make this extremely narrow, focused, and really good at doing one thing very well, and anything that is really not part of this should be kept away from that. And that helps us to really create a code that is easier to maintain, and this gives us the ability to really focus on a context and a bounded context and then narrow that particular abstraction. Now we may wonder, why shouldn't we really have things that do multiple things? Well, imagine for a minute I'm writing a class, and let's say this class is involved in doing some logic calculations. It also has to go out and get data from the web and parse the data. The data may come in a SOAP XML format. It could be a raw XML. It could be a JSON object. It could be a comma separated values. It doesn't matter. It gets the data, parses the data, applies the logic, the algorithms, and processes the data, and then now it generates a very detailed format of how this result must be represented. Sometimes we call these kinds of code as a ball of mud because it does everything, and you poke at it, immediately fizzles out and becomes very difficult to put it back together. But take this example for a minute. Now, if you take this example where everything is mixed up together, where you have the logic, the intense logic of processing the data, the parsing of the data, the manipulation and the formatting of the result, everything being done together. Now, tomorrow, let's say, the service we depend on modifies the data format. Our code no longer is going to work because the data format the code expects is no longer the format that the data is coming from. So we have to change this one class now, which means we got to wade through this class and start modifying it. And as you step through this class now, you have to wade through and walk through, for example, the code that is dealing with logic, the code that's dealing with the formatting of the display data, and then the parsing data. All of that is in front of you, distracting you when you should really be focusing on only the code related to parsing the data. 2 days goes by and they decide to change the format of the data we want to display. Once again, we have to wade through all that logic. But on the other hand, imagine we made the code very cohesive, where you have one small piece of code that is going to talk to the web service to get the data and parse it. Another small piece of code that is doing the intense logic and algorithm and manipulation of the data, and yet another small piece of code that is doing the formatting of the data. Let's say we have this code in 3 different pieces, 3 different small classes, and a few months goes by and the data format changed on it, or we are told we should talk to 2 different services. We can leave the first 2 classes intact, one that displays the data and one that does the computation, and very nicely we can either go work on the piece of code that's only doing the parsing, or we can even come up with the alternate implementation of it. We could even come up with multiple simultaneous implementations we can switch between depending on the service we want to talk to. A few days later, let's say the data format has been modified, or they tell us we need to support 2 different data formats to display the data, maybe one in English, one in Spanish, and maybe one on a UI, one on a console. Well, we don't have to really worry about anything. We can just go ahead and create alternate implementations of the view or the data format for the display, but the remaining 2 classes remain intact. So making code very cohesive makes the code easier to extend because the change becomes a lot more localized, and when we get in to modify the code, we are able to focus on one area and modify the code in that particular area. So if there is 2 things we can take home right now, and that is a good design has high cohesion and low coupling. So you want to create a code, a design where the cohesion is very high and the coupling is very low. And when a high cohesion is there, then it just crystallizes the code and it becomes really small and focused and tiny little thing that does one thing and one thing well. High cohesion is when it really becomes small and focused. Low cohesion is when it dilutes and bloats up and then just kind of spreads around like a blotting paper. You put a drop of ink on it, it just bloats out. That's low cohesion. It spreads and becomes big and tries to do a lot of stuff, takes a lot of surface area, whereas a very highly cohesive code is very narrow, focused, and does one thing and one thing well. Likewise, high coupling is evil. High coupling means your code depends on a lot of things, and it also depends on very strong dependency on things. Whereas low coupling means you depend on fewer number of things, but also the things you depend on are much more lightweight dependency, like an interface rather than a concrete class, and so on and so forth. You can also think about the Pascal's law we talked about earlier, where you could say that you want to be very generous in what you receive, so that way you can vary the implementation. That kind of comes back to the loose coupling as well in this particular context. So that is an example of how we want to really work towards high cohesion and low coupling. We also, when it comes to designing classes, we have to try to come up with 3 other metrics to think about: sufficiency, completeness, and primitiveness. Now, it may be a little confusing in the beginning when we put these terms together, but let's kind of discuss about and see what these things actually mean. Primitiveness simply really means that the methods, the operations we provide on an interface, on a class, are really very small and basic implementations, and they are really focused towards providing efficient implementation for whatever functionality we want. So given a function, you ask yourselves, is this function very primitive, something that is very efficient, and something that cannot be built using the other functions available in this particular abstraction? For example, if you consider a list, adding an element to a list is very primitive. You must be able to add an element to a list. But adding 10 elements in one shot to a list may not be really as primitive, because you could have implemented that with other functions, hopefully efficiently also. So you may argue that that's not really primitive, that may not be necessary. So when it comes to functions, always try to provide minimum number of functions, and also the functions that are primitive, methods that are primitive, that is something we should try to provide. But then when it comes to creating methods themselves, there's a balancing act between sufficiency on one side and completeness on the other. For example, when you have a little class with a certain methods, you say that the class is sufficient if it has got the ultimately minimum number of methods in it. You also say the class is complete if you can do whatever the abstraction needs from you. So for example, let's say I have a list again to talk about, and the list has an add method, and the list also contains a remove method. So I can add an element to the list, I can remove an element from the list. At this point, the class is not complete. And the reason the class is not complete is I can add an element, I can remove an element, but I don't have a way to tell whether an element is already in the list or not. And that's a very basic operation I would like off of the list. So I may argue for my list, I need to add an element, I need to remove an element, I also need a function or a method to go off and look if an element is contained or present in the list. Now that I have these three methods, we could say that the class is complete and it is sufficient also. Now I could come in and add a method called add two elements, and the code will still be complete because it was already complete. But it is no longer sufficient, it is more than sufficient. So in other words, sufficiency says that keep it minimum. If you really want to think about it in a different way, think of a line, if you will, and on this line, there is a point on the line which is a point of complete and sufficient. You go to one side of it, you are not complete anymore, and you go to the other side of it, you are not sufficient anymore. So right at that point you are complete and sufficient. For example, if for the list the point is right here on that line, I could say I have an add and I have a remove function, but the code is not complete right now because there is no function to see if the list has an element, contains an element. Now I add a function called contains an element in addition to add and remove. Now my list is complete and sufficient. Now I add an extra method to it to add a couple of elements. Then the code is no longer sufficient. It is still complete, but it is not sufficient. I got to remove some to become sufficient. I got to add some to become complete. So you can say that you keep adding stuff to make it complete, but there comes a point when you cannot add any more for it to be sufficient, and if you add some more, you would have to remove it to become sufficient. So these two things pull in the opposite direction, and as a result, it keeps the abstraction in balance. By being complete, it does everything that should be done, and it is sufficient. It does only what's absolutely necessary. So when it comes to designing the methods of your abstraction, your classes, think about completeness, what am I missing, and think about sufficiency, what am I doing that's not really needed, and I could remove it, and maybe from the outside I can do it using a facade. I could come in and call those methods. Now, one aspect we need to be careful about here is efficiency. If you can not just guess, don't predict, don't have bias, but if you can show that having this method as a member of this class makes the code far more efficient, not in belief but in practice, then you can have an extra method in this class, because that implementation is still sufficient because its presence is making the code very efficient. But if you remove it, you can still implement it using the basic functions, but it won't be as efficient, so you can bring in the efficiency. But very important, don't use your bias, don't use your emotions in making this decision. Only bring in a code into the class which can otherwise be done using other functions, but only when you see performance gains, not ahead but later on. So at first, implement it outside, use in a facade, in a helper class, using these primitive functions, and if and only you see performance degradation, then bring that inside to this class to provide that efficiency. And so in that context, you could bring in an extra method, because even though that's not necessarily needed, it could be done using other functions. It makes the code a lot more efficient. So when it comes to design metrics, think about coupling, think about cohesion, think about sufficiency, think about completeness, and think about primitiveness of the code. And these things can help us a great deal when it comes to developing software, better quality design of software. So we talked about some of these metrics. I want to talk about one other principle or a law that we should keep in mind, and that's called the law of Demeter. The law of Demeter says methods of a class should not depend in any way on the structure of any class, and I'm going to add the word internal structure. So methods of a class should not depend in any way on the internal structure of any class, except the immediate structure of their own class. So in other words, when you write code, do not make your code depend on the internals of the classes you depend on. Your boundary stops in the classes you depend on, not what's behind those encapsulation boundaries. Furthermore, each method should send messages to objects belonging to a very limited set of classes only. Now, if you really think about this, you can draw a line right after this own class period and read just that first sentence. Methods of a class should not depend on any of the structures of the classes, any other classes, except the immediate structure of their own class. What's that? That's talking about encapsulation. So the law of Demeter simply is a combination of encapsulation and low coupling, good encapsulation and low coupling. The second part says you should send messages to a very small set of classes. That is saying, let's lower the coupling. So law of Demeter simply encourages us to honor encapsulation and lower coupling when it comes to design of classes, and that's another thing we should follow when it comes to developing software. So as you're writing code, make sure that you don't try to breach encapsulation boundaries and start talking to internals of classes you depend on. Sometimes we tend to do this. We should avoid that. And second, we should also try to make sure that we minimize the interaction between objects. If you're writing one function that requires talking to 7 objects, try to modularize it so the functions, each of them, either talk to minimum number of objects, or even better, you pass the data it needs to it, so the function itself doesn't have any dependency, and you can remove the dependency, and that makes testing easier as well, and designing also less brittle. The design becomes easier to evolve as well. So we talked about a few metrics, and we talked about a law of Demeter. One first principle that I want to talk about here is called the tell, don't ask principle. The tell, don't ask principle says procedural code gets information and then makes decision. Object-oriented code tells objects to do things. This is essentially a tell don't ask principle, as Alex Sharps talked about in Smalltalk by example. And he says that we should really rely upon giving responsibility to objects rather than querying and making a decision on things. In other words, objects should take limited responsibility and rely on other objects to provide the appropriate service. And so this leads to the command query separation pattern. Objects have query methods where they give you data and command methods where they do some actions. When it comes to modeling, it's important for us to not get into this mess of really getting data, making decision outside, and simply propagating a command to the object only for it to update its state. Instead, give responsibility to objects. Let's consider a couple of different examples here. I'll start with one example by my good friend David Bach, and he talks about this example of a paper boy. In one model, where it is failing the law of Demeter and also fails the tell don't ask principle, is the paper boy has a method where he wants to go get money for the paper boy is delivering. So he goes to the customer and says, knock knock, I'm here to get paid, I want money for the paper I've been delivering. The customer says, oh, of course, but I'm pretty lazy right now. Do me a favor, Johnny. Walk right through the door, walk all the way to the end to the kitchen, and in the third shelf, open the drawer, and there's a cookie jar, and within the cookie jar, there is cash. And the paper boy, of course, now drives away in his Jaguar. And the point really is, you don't really open up the wallet or tell where the money is. That's your business, that's your encapsulation boundary. So the paper boy can only ask you for money, but it's for you to really give the money or do whatever you have to do. In the case of honoring this, the customer.getPayment method the paper boy calls, and the customer controls how to really get the money and return it. So that is something for us to think about in terms of how we model this, is we need to really say, hey, the responsibility of giving the money is the customers, and you cannot let the paper boy breach that boundary. Here is another example to think about. When it comes to, let's say, modeling, I could model a person object. I could have an age on the person object. And then I could say, hey person, what is your age? And I can then check the value of age, and then I could say if the age is greater than 18, greater than or equal to 18, then I can turn around on the person and say, vote. So I make the decision whether a person can vote or not external to the person object by providing this method to get the age and make a decision and then set back. But on the other hand, what if we write a method that simply says, please vote, and the person object internally decides what the age is, and if they are of legal voting age, they can vote, otherwise they reject the request to vote. So in this case, you tell the object to do something rather than asking the object for some data, making the decision outside, and then going back in and modifying this, or modifying the state, or giving a command at that point. Now you could say, well, is the responsibility whether they should vote or not, is that a person's responsibility or a separate voting logic responsibility? That's where things get a little tricky and confusing. Well, after all, if there is a method on the person that says the person will vote, then that decision should be within the person. But if the person doesn't have a function called vote, but if an external object is going to carry out the voting for the person, then that decision should be in that object along with the function that does the voting. In other words, do not separate the decision making from the action. They need to be in one shot. You tell and it makes a decision to carry it out, rather than you ask for hodgepodge of different disparate data and then make a decision and then communicate that back with a function to change the state or carry out an action. So that is something to think about when it comes to the law, tell, don't ask. So we talked about a few metrics. We talked about a few ways to think about code separation and coupling and the law of Demeter. And we also talked about one principle here, which is the tell, don't ask principle. Now we're going to get into more code examples and start looking at more concrete pictures and examples. But let's talk about one more thing before we wrap this up. This is called the train wreck pattern, where you end up doing things like this. You have a customer get address, get city, get county. When you look at this structure, often this is called the train wreck pattern. Don't confuse this with more of a modern functional style notation. Well, I say modern because we are beginning to use it, but it's been around for a long time. But more functional style approach where we have a function composition, where you take a list and you say stream and filter and map and reduce. That is very different than what we are talking about here. In that case, we are at the top level of abstraction where we are transforming a list into another list into another list into another list. That is perfectly okay. Whereas here, we are not transforming, we are digging way deep into this abstraction. Notice the code here says, customer.get the address of the customer, get the city, get the county where the city is, and this keeps on going. What does this tell us? Well, first of all, this code is really hard to understand because you got to sit there and say, oh, I'm going to go through all these layers to make a decision. This is hard to debug. It lacks cohesion because you can see this is all spread out and not very focused. It is also very coupled and very difficult really to work with. This is a candidate for refactoring. But what does this really tell us? This tells us the code up here, way up here, is making a decision based on a logic way down there. So this is like me saying, when I have several people in front of me, certain things I will say is based on maybe the color of somebody's eye and that person wearing a blue shirt. Well, that's incredibly stupid because this high-level decision is trying to make a decision on such a low-level detail that I have to transfer many levels of detail to get to it. If you have a situation like this, it's time to refactor it. But the question is, how do you go about refactoring this? Well, the way to go about refactoring this is really to say, if I really am making a decision here that requires that low-level decision, it simply means that I need to redesign my system in a way that decision-making property is not way down over there, but it's at the top level. So for example, if a decision I'm making here depends really on a size of the county, well, the size of the county should probably be here with the customer, where the customer resides, and not have to go through all those layers. So we don't want to, this is where the domain and the context again comes back. We don't want to literally model it based on, here is how purely the domains are related. Sometimes you would bring in a cross-cutting concern all the way to the top because it makes the access over here a lot more efficient and also meaningful. So the data, the way we model the data should be based on the actual usage of the data and not the purity of how the data is actually, perceived in our minds. So we'd have to redesign this to make that happen. So we looked at some design principles in this part. We're going to get into a lot more design principles and a lot more code examples along the way as we get into, and we'll start typing some code and playing with it. So get back to the next part of this presentation where we'll continue our discussions on design principles.